Hi guys, here's the other main project I've been working on lately. It's an AC drive system for an electric car. Sort of a very lashed up prototype. It's a control board that controls an inverter power stage, a whole bunch of IGBTs, like 22 IGBTs in parallel on each leg. This can run to about 360 volts at 300 amps peak, as long as you can keep it cool. And three-phase goes out down here to a motor generator set. That's the AC motor, which is a rewound 1 horsepower Lincoln Electric motor. I rewound that to run. It was originally 240 or 480. It's been rewound to run 24 volts nominal at 60 hertz, and it's coupled to a 9-inch Kostov Sepex DC motor as a generator. A couple of chargers over there in power supply mode to run the field, and the armature connections supply power out back up here through a diode onto the bus. So when the motor goes fast enough, the generator generates enough voltage, and it just supplies the power back onto the inverter. So the power supplies over here only have to keep up with the losses. The control circuit consists of a DS-PIC digital signal controller running pretty much an application note software that Microchip released for AC induction motor vector control, modified a bit so the field weakening works a little bit better, so it actually looks at the output voltage and regulates the field strength to get the maximum inverter output voltage. There's a connection going out here. Those are the 3-phase gate drive signals going out to the gate drive card here with a bunch of some high side drivers and some high current 14 amp buffers. What else we got? On the motor down here there's let's see if we can see this, a encoder to measure the speed. That just wires run up for here to a detector circuit comparator, and there's also current transducers, one on each, or two on A and C phases, and those run over to an amplifier, and some amplifier sends the signal to the ADC, and there's a hardware comparator circuit that will shut the output down if overcurrent is detected, independent of the micro. And I'm sure that has saved the power stage numerous times. The power stage consists of 132 12N60 IGBTs in parallel, lots of internal diodes. 20, as I said earlier, 22 per leg. That's good for about 450 amps peak, 300 amps RMS approximately output per phase. Yeah, they're just 6 stacks all the way across, clamped down. Little bits of, probably be difficult to see this, but there's little bits of rubber underneath the between the board and the IGBTs, clamped down with plastic screws, and there's a capped on film with thermal conductive paste or phase change material on each side to get the heat to the heatsink. There's also a temperature sensor, so the micro knows what temperature the heatsink is at. I don't really like how I built this. I built this power stage a while ago, and I wouldn't build another one like this. I'd use individual large IGBT bricks. This is way too much labor to assemble, and there's too much chance of a little speck of conductive debris piercing the insulation under one of all those FETs or IGBTs. I think that'll be the next project, is to build a proper power stage. Okay, let's give this thing a run. Turn on the DC bus, we're up to about 50 volts, and push the throttle up. And there we go. I've got the force gauge mounted to an arm that's 1 foot radius out from the shaft center. You can see the torque. It's zero torque, it's at about 1.5 foot-pounds. Get up to speed, and eventually we'll hit the point where the motor starts generating. There we go. Now we can actually produce some torque. And the power supplies are maxed out right now. Change there. I think there's a bit of a problem with noise on this layout. Let's try that again. There we go. Yeah. Anyway, we can get about around 10 foot-pounds or so out of it. With these power supplies, which supply about 40 amps. And we're generating, let's see, generating about 40 amps at 50 volts. So what power would that be? So 40 amps at 50 volts is 2 kilowatts. That's a little bit less than 3 horsepower. But that's not including the efficiency of the generator. It's probably a bit over 3 horsepower coming out of the motor. Now let's take a look at the waveforms. The yellow is the gate drive to the A phase, and purple is the output current measured by current sensor, current probe over here. That's at 50 amps per division. So let's start out DC, and as we go up in frequency, eventually the voltage, output voltage, current drops because we don't have enough voltage to get the current any higher at that speed. And now we're producing 40 amps output on the generator. Let's zoom in and look at it triggering now. A little bit of waviness in the current, which I think is from the slots of the stator. As the magnetic field crosses, it's not totally even. You can see we're getting up pretty much to 100% duty cycle. We've got a feedback loop looking at the output voltage and regulating the magnetizing current to keep the PWM peaks at about 100% to get the maximum possible use out of the inverter. Let's go for more power now. Still pretty good sine wave, not the best. I need to probably adjust some of the feedback loops. It's a bit, I set it quite slow so it's stable. It's still using pretty much 100% peak duty cycle. You can see the little sort of bits in the middle. It's outputting a little bit of third harmonic, which again, to maximize the possible use of the inverter. If you do the math, adding a bit of third, I think it's 1/6 third harmonic, maximizes the output voltage of the inverter for a given DC bus voltage. And now we're down to a range where it's in constant magnetizing current, and their PWM is less than 100% at the peaks. And let's shut it down. Okay, let's see how much torque we can get out of this thing. I've stalled the generator with a vice grip, and now we can turn on the power supplies and apply some power. Pretty good. Let's see what kind of current we're getting. Of course, we're getting very low frequency. Let's go to roll. Now that's a low frequency. And we're overloading the current probe too. Let's see what kind of torque we're getting out. Again, subtract about 1.5 from whatever the reading is. power supply gave out there. But about 24 foot-pounds, 22.5 foot-pounds. And remember that this motor normally puts out about 3 foot-pounds. It's a 1 horsepower, 1725 RPM motor, so that's about 3 foot-pounds nominal. So that's quite a bit of torque. And we're limited again by the power supplies. We can get even more torque if there's more power. I hope you found this video on the AC drive system interesting. If you want to know any more about it, want me to make another video or go into how vector control works in more detail, please let me know. Anyway, thanks for watching.